Okay, good morning. I make it a couple of minutes past 8 o'clock UTC. So we're going to make a start on this webinar for transient electromagnetics. So I hope everyone can hear me. Right, I'm going to start today just by giving you a little bit of background about myself. My name is Jimmy Adcock. I'm a geophysicist by training, studied geophysics at university. I then worked for 13 years for a near-surface geophysics company in the UK, and I then left there and joined Guideline Geo. And normally I say, oh, about 3 or 4 years ago. But today I actually know it was 5 years ago today. So at this very moment in time, I would have been walking through the doors of Guideline's offices in Sweden for the first time. So very easy for me to remember how long I've been in the company today. I'm currently, I joined as an application engineer. And at the moment, I'm part of the team looking after the ABEM products. And it's one of those that we're going to be talking about today. I thought there may be some people in the room who have just kind of been brought in by the prospect of learning a little bit about transient electromagnetics, about TEM. And maybe you don't know Guideline Geo that much, so I'll give you a little bit of background about the company. I apologize to those who do know us and those who've sat in these webinars before, because we always put a couple of slides in on this. But Guideline Geo, we offer geophysics solutions, and we have products in GPR range, which is the Mahler brand, and then Resistivity, Seismics, and TEM under the ABEM brand. All of our manufacturing, our research and development, and our head offices are in Sweden, but we have technical and sales offices right the way around the globe, as you can see from this image down at the bottom. So we cover most of the time zones pretty well. And in terms of the history of the company, well, it actually goes back a very long way. ABEM was founded in 1923, and even back then they were starting to develop electrical methods to prospect for minerals primarily. And then from there, it's developed over time. The Mahler company sort of came into being in the 1930s. It was sort of part of the Swedish Geological survey, and then kind of grew into a private company, and the office was based in a community called Mahler, so that's the name, right up in northern Sweden. And this slide just shows kind of when our key products have been launched since then. And as you can see, we're very close to coming up on our 100th anniversary, which will be a very, very exciting year to be a part of the company. Right, so let's get on with what you're all here for. Let's talk about TEM. So today we're going to just talk about the theory behind the method. And as we said in the outline for this, it's kind of aimed at people who have either a very low level of knowledge about TEM or have never used it at all. So we're going to start pretty basic, but we'll cover the theory in some depth. We're going to then look at the WalkTEM family of instruments. So look at the products, what they can do, how they do it. Then there'll be a few data examples just to give you an idea of the kind of stuff you can get out of this methodology. And then a very quick look through some of the software that we use for processing the data. And the software that we'll be using all comes from a company called AGS, that's Aarhus Geosoftware. They're based in Denmark, and we have a very good working relationship with them. And so that tends to be the software that we would always recommend to use with our TEM systems. So TEM itself, what does it do? Well, it's a method to measure the ground's conductivity. And because conductivity is simply the inverse of resistivity, we actually present the results as resistivity values. So it's a means of us being able to map the resistivity of the subsurface. We kind of keep it in the resistivity realm because that fits nicely with our other product, the ABEM Terameter LS. And primarily for TEM, you're looking at applications where the target feature that you're looking for is conductive. Because it's responding to conductivity, it's very good for mapping groundwater and very good at identifying mineral bodies. Another big advantage of TEM is it's what we call an inductive method. So unlike a resistivity survey where you have to physically put metal electrodes into the ground to inject the current, with a TEM system, we actually lay out wire loops on the surface and we induce a current into the ground. So it doesn't have to be a physical connection. And that can be very useful in regions where you have a very, very dry, very resistive top layer, where you might struggle to get a good electrical contact with a traditional resistivity system. Those loops are causing an eddy current to flow in the ground. That's called a transient. And that's basically generating the response that we can measure from the surface. And that response that we measure from the surface is what's going to tell us about the conductivity, resistivity of the ground itself. So a typical layout would look like this. We have an instrument at one corner of a large transmitter loop, and that's generating our primary signal. And then in the center, we have our receiver loop or receiver loops. We can have more than one. And that is then capturing the response of the ground. And that's what's going to tell us about the subsurface. So how does it do it? Well, we go back to some very basic physics to start with. And that's the principle that if you have a loop of wire with a current flowing through the loop, that will generate a magnetic field. And in all the textbooks, it generally looks like this. You have a ring with current flowing through it, and these nice lines of magnetic field that are set up around that ring. And what happens is that if we very, very quickly switch the current off that is flowing in that loop, that green magnetic field collapses very, very quickly, and it generates what we call an electromotive force, electromotoric force. So that is a pulse of energy, and that energy has to go somewhere, and it can't go into the air because the air is non-conductive. So it goes into the next thing it can find, and that's the ground. And the way to think of this is that if you imagine a tube of water, an open tube of water, and in that tube of water you have a fast flow with nothing to stop the flow, it continues all day quite happily. But if I was to suddenly put a barrier in there, you would end up with a big splash back. And it's not an exact analogy, but it kind of works quite well, because if the water is flowing faster, when you put the barrier in, you'll get a bigger splash. If you put the barrier in slowly, you'll get a very small splash. And if you put it in very, very quickly, it will be a big splash, a big pulse of energy. So that's kind of the principle we're working on. We want to stop that current in the loop as quickly as possible. So as I say, in the real world, we're talking about a loop of wire on the ground carrying the current that we're going to cut off very quickly. When we're generating that signal, when we're making that current flow and then cut it off, we actually repeat that time and time again, because the pulse that we make is quite big initially, but it dies off very, very quickly. So the signals that we're trying to record are very small. So what we want to do is we want to repeat the measurements hundreds, if not thousands of times, to get a very, very good, clean return signal. And when we're doing that repetition, we don't want the current to always be flowing in the same direction, because if we were to do that, then there's a possibility that we would just end up charging the ground up and changing the response that we get during the measurement. Whereas we want to keep the ground in kind of its original state, or as close to it as possible. So what we do is we inject the current in one direction, first of all. So we switch the current on for a pulse, then switch it off very quickly. And then we take our measurement, see how the ground is responding. Then we switch the current on in the opposite direction, let it stabilize, then switch it off, and then measure the response again. And by putting the current forwards, backwards, we don't ever charge the ground up too much in one direction. So theoretically, every time we take the measurement, we should get the same response back. So yeah, it's eliminating what we call drift. Now, again, in the real world, things are never quite as simple as they are in a PowerPoint presentation. So when we're switching our current on and off, we can't actually do it very quickly. There's what we call an on ramp. So we turn the current on and it slowly builds up in the loop. And then when we switch it off, we can't make it disappear completely as soon as we switch the transmitter off. And again, if we go back to our water analogy, our water example, if you think of a hose pipe full of water, tap is on, water's coming in at one end and flowing out of the other. If I was to suddenly switch that tap off, the water wouldn't stop immediately at the far end of the hose pipe. Water would flow for a short amount of time afterwards. And it's the same with our loop. We switch the current off as quickly as we can in the transmitter, but some residual current will still be flowing. And it's whilst that current is being switched off that we generate the electromotoric force, the energy pulse that's going to be transferred to the ground. And if that pulse is being generated, then at that point we are unable to take a measurement because that pulse is just going to swamp our receiver circuits. So we need to wait until all of that current, that pulse, has disappeared from the loop, and then we can begin to take our measurements. Looking at it as it might look in the field, we've got a very simple setup here with a transmitter loop in red and the receiver loop in orange, and then our instrument off to one side. Now, what we do is we're pulsing the current around the transmitter loop forwards and backwards, forwards and backwards. But if we look at that at one point in time, whilst the current is flowing in one direction, then we have this magnetic field set up, which is shown in yellow. Then when we switch the current off, that magnetic field collapses, and that causes these eddy currents then to flow in the ground beneath the loop. And they gradually spread out, getting deeper and deeper and deeper. Quite often in the textbooks, it's referred to as the smoke ring effect. So it spreads out, gets wider and wider. And then that eddy current that's flowing in the ground will generate its own magnetic field because it's effectively a current flowing in a loop. And it's that secondary magnetic field shown in white here that our receiver circuits are going to be detecting. So you can take a setup like this and you could measure down to 100, 200, 300, 400 meters, depending upon various aspects of how the instrument is set up. And you can do that in just a few minutes. And if anyone has ever done a VES survey, a traditional 1D resistivity survey, you'll know that to get to any given depth, you need to spread your electrodes out to approximately 5 times that distance. So if I wanted to reach 100 meters, I would need to take measurements starting at the center where my instrument is, gradually moving out until my electrodes are 500 meters apart. So a VES measurement is quite slow and laborious, and compared to a TEM measurement where you're talking about maybe 20 minutes to lay out the loops and then a few minutes to take the sounding, it suddenly has a lot of advantages attached to it. So apart from just being able to put more current in, as we talked about when we looked at the pipe example, to make our pulse bigger, make that splash bigger, we can also control how the instrument responds to the ground by changing the loops that we're using. So if we use a larger transmitter loop, so the current is enclosing a much larger area, when we switch it off, we get a bigger pulse. So we get that bigger pulse, then we can theoretically be able to see much deeper. With the receiver loop, if we make that smaller, then it's going to be more sensitive to changes near surface, because what happens is that the field changes very, very rapidly at first, and then it gradually gets slower as it gets deeper. So to be able to record the stuff that's near surface, we use a very small loop that can respond rapidly. But if we make the loop bigger, then we actually can enclose more of that secondary field and therefore detect smaller, weaker signals from greater depth. So we often need to think about the size of the loops that we're going to be using based on the application that we have at any particular survey. Once we've got that simple response, what we would call the apparent resistivity curve, back from the instrument. So that is the response that we've recorded from those secondary fields. We can then invert that to give us a 1D model of resistivity. So this diagram here is showing resistivity on the red line against depth. So we've got depth down the side, resistivity along the bottom. So again, anyone who's done a VES survey would recognize this as being the similar output to that kind of survey. If you haven't done a VES survey before, or you're new to geophysics, then I should probably explain how we go from this sort of ground response to a model of resistivity against depth. And we're doing that with what we call inversion software. So this is software that tries to guess what the subsurface looks like based on our real world data. So we have our TEM system set up here with our transmitter and receiver. And it's taken its measurement. And from that measurement, we have a series of values for apparent resistivity at increasing depth. And so we have our sounding curve. So depth down the side, apparent resistivity across the bottom. And the reason it's called apparent resistivity is that if we take a measurement at the surface, then all of the layers beneath are going to be having some kind of impact upon what we measure. So for example, this bottom layer, the eddy currents have passed through the top 2 layers to get to it. And so they will have impacted the response that we get. So we need to somehow work back to the true resistivity values for each of these layers. And the way we do that is that we load the raw data into the inversion software. The inversion software creates a model of what it thinks the ground looks like, and it does a synthetic survey over the top of that model and looks at what the data coming back would look like. So this first model, it does the synthetic survey, and it finds that the data that would have come back looks nothing like the data we have brought back from our survey site. So it says, okay, I need to change the model slightly. So it maybe adds another layer in, and then suddenly the curve looks a bit closer to what we brought back from the field, but still not quite right. And so the software will continue changing, tweaking that model until it gets a curve that is very similar to our real world data. And at that point, the assumption is that this geological model is something close to what we had in the field. At the end of this process, the software gives us what we call a residual, and the residual is telling us how closely those 2 curves follow each other. And it's usually given as some kind of percentage or a decimal value. And if the number is very low, then that means that the 2 curves sit on top of each other very, very closely. And if the number gets bigger and bigger, then that means that those 2 curves are slowly spreading apart. So we're generally looking for lower values to imply that that model is more reliable. And we'll look at that again a little bit later when we look at the software. So once we have that model of resistivity against depth, then we can start to apply our interpretation to it and get to the useful output, which is, you know, what is the geology here? Where is there, say, for example, fresh water? Where might there be a mineral body? Where might there be saline intrusion? Those kind of things. So just a little bit more now about kind of what happens in the ground in a more scientific way underneath our loop. And this is a view of the current that's flowing, of those eddy currents that are spinning round and round in the ground. And the blue and the red are showing you kind of the positive and negative sides of the loop. So what you need to imagine is that there's a circle of current coming out of the screen towards you, and it's coming out from the red side and back into the blue side. And so you can see that over time that gradually spreads out into the ground. And what you can see is that it spreads out, it becomes very large as it gets deeper and deeper. So we lose resolution once we get to any kind of great depth. So we're not going to be defining very thin layers with this methodology, certainly not at depth. But if I now move on, what we can also see is that if you look at the time here, this time is being plotted in a log sample method. So that means that when it first starts, each new image is 1 microsecond. And then as it gets further on, the jump in time between each new image gets bigger and bigger and bigger till at the end it's jumping by 100, 300, 400 microseconds. And what that tells us is that the current moves really, really quickly when it's near surface, and then it moves much slower when it's down at depth. So it's very difficult for us to measure those very near surface values, because if we were to plot that in a more normal way with just a linear display of time, so this is the same plot, it's just that we're showing each image for the same amount of time, you can see that the very near surface changes are very, very fast. And that's the complicated bit about TEM, really, is being able to design something that can cope with being able to measure these very fast changing values at the start of the measurement, and also cope with these very weak signals at the end of the measurement. So if we talk about what happens when we change the resistivity of the ground, we can actually start to see how those eddy currents behave. So with a very low resistivity ground, so we just pretend that this is the subsurface directly beneath the instrument, and that it's completely homogeneous, it doesn't change at all, and that it's only 10 ohm meters, so low resistivity material directly beneath the loop. You can see that the current moves very slowly through the ground. If we then increase the resistivity of that layer to 100 ohm meters, actually it starts to move a bit quicker now. So if you compare the two, you can see that the smoke rings, those eddy currents, they disperse much, much faster in the high resistivity. So the current tends to stay in the low resistivity stuff. It's quite lazy. It likes the high conductivity, low resistivity materials. And that's really why TEM is best for determining, detecting bodies that are very conductive, like water and minerals, because the current will sit in them for a relatively long time, making it easier for us to see them. So if we have two different layers, if we have a low resistivity into something that's high resistivity, what we'll see is that the current, again, tends to stay in that low resistivity zone, and we don't get very much current into the high resistivity. And the impact that that would have on our measurement is that we would be able to detect this boundary with some certainty, but it would be very difficult for us to determine what the resistivity of that higher resistivity unit is. All we can say is it is much higher resistivity than the material above. If the scenario is reversed and we have higher resistivity near surface, lower resistivity at depth, then the current moves very quickly through the high resistivity, and then it hangs around in the lower resistivity deeper unit. So again, this is allowing us the ability to see deep conductive bodies much more easily. So like an aquifer, like a mineral deposit, like saline intrusion. So this is very good for TEM. This is the kind of a good geological situation for us to be in. Problematic for us would be if we have something that is quite resistive and also quite thin within our geological section. So here we have 100 ohm meters at the top, 30 ohm meters in the middle, back to 100 ohm meters, and then very low resistivity 10 ohm meter unit at the bottom. And so the current kind of passes relatively quickly through the 100 ohm meters. Then it gets into the 30 ohm meter and it sort of sits around in there for a while. And then effectively it jumps the third layer. It jumps that high resistivity layer because it's difficult to induce a current into that, but it's very easy to induce the current into that bottom 10 ohm meter unit. So we need to be aware of the fact that as a methodology, it's not going to be well suited to defining thin, high resistivity layers. That would be, you would be better off using a resistivity system for that. So if you look on the side, this is what our sounding curve would look like. So we've got layer 1, transition, sorry, layer 1, transition, layer 2, transition, and then we just see layer 4, and layer 3 is not well represented. A question that we get asked quite a lot is, how deep can you see with TEM? And the problem with answering that is that it is very, very dependent on the geological conditions and the amount of electromagnetic noise that's in the environment. As I said, these are very weak signals that we're trying to record. And so if there are any sources of noise around the survey area, then that will limit how deep we can record the data. This table was produced using some very simplistic models of the ground subsurface. So this was produced by just saying, I have a loop at the surface, and then I have a block of completely homogeneous material of a given resistivity. And so what we've done in this table is change the transmitter loop size, so 40 by 40 loop, 100 by 100 meter, 200 by 200 meter, and then also increase the amount of current that flows in that loop. So as I said in the beginning with the pipe analogy, if you have more water flowing in the pipe, when you put that stop in, you get a bigger splash. Same with the TEM, if we put more current in, we get a bigger pulse, and therefore we should be able to see deeper. So by increasing loop size and increasing current, we increase the pulse size. And what we can see is that as we increase current, then the maximum depth will increase. As we increase loop size, the depth increases. And as we increase the resistivity, the depth will increase. So this table is kind of a culmination of everything that we've just looked at, because it's showing us that, yeah, bigger loop, bigger pulse, more signal, bigger current, bigger pulse, more signal. They allow us to look deeper. If the resistivity gets higher, the eddy currents will pass through it quicker, and therefore we should be able to see deeper. But generally, it is very, very difficult to say for definite. You know, that there are no real hard and fast rules of thumb as to how we can compare, say, current and loop size to ultimate depth. And so modeling it is really the best way we can do that. I mentioned then that noise is a problem, and that noise will largely control the point at which we lose the signal. So it gets lost in just the background electromagnetics. So there are a whole host of sources of noise, and some of them we can deal with, and some of them we can't. So starting with the ones we can deal with, we have general electromagnetic noise. So that's coming from mobile phones, television transmissions, radio transmissions. They tend to be, we can filter those out. If, for example, if it's just random electromagnetic noise, if we repeat measurements over and over again, the random nature of the noise means that over time it will cancel itself out, whereas the signal that we are generating is the same every time. So it just gets bigger and bigger and bigger each time we repeat the reading. So we can deal with that. We might get noise from the electricity transmission in your national grid. So, you know, we have these big overhead lines, we have buried cables, we have transformer stations, and all of these are actually leaking electromagnetic noise into the environment. But we know what the frequency of that noise is. You know, it's either 50 hertz or 60 hertz, depending upon which country you live in. So we can filter that out, so not such a problem. We get natural sources of noise. So these are things like fluctuations in Earth's magnetic field. It's lightning in storms that could be, you know, thousands, hundreds of kilometers away. But again, that noise is random. So if we repeat our readings, we should be able to reduce the effect of that. And then there's always going to be some kind of instrument noise that is from the components that we're using. And that's true for any TEM instrument. But again, those we can get rid of by calibrating the system during the setup of it. And so again, it's not something we need to worry about. Problematic ones are what I would call natural noise. And noise probably isn't the best word, but we're taking a 1D sounding. So we're just measuring resistivity straight down, and we're assuming that that's coming from directly beneath the center of our loop. The assumption that we make when we do a measurement like that is that the geology doesn't change significantly anywhere to the side of our loop, and that any layers that we detect are completely horizontal. And that isn't necessarily going to be the case. In fact, it would be quite rare that that is truly the case. So, for example, if we were to take a sounding here and there was a very, very high resistivity body just off to one side, that would impact the data that we record. And so we need to be aware of the fact that we may not be getting a true measurement of what's directly beneath here. And we can't get rid of that. All we can do is measure in a couple of locations, for example, to test it, or even measure different components of the returned field. So we can measure a vertical component or horizontal components, and they will be different depending upon whether we have a 3D body underneath of us or a very simple 1D situation. And then the final one, which can be problematic, is coupling. And this is where our transmitter is actually inducing current in surrounding buildings and infrastructure that are close to the survey area. And this is probably one of the things that you need to consider about the TEM method, which is that we get these problems with infrastructure. And so our survey sites need to be free of things such as telephone wires, buried cables, buildings, that kind of thing. So this first type of noise, called capacitive coupling, this is where we actually induce current into an insulated conductor, so like a buried cable. And what happens is that as the current is flowing around the loop, it's inducing the current into this isolated conductor in the ground, and it basically acts as a second loop. And what happens is that the current in it oscillates backwards and forwards as it keeps discharging into the ground and inducing more current into it. And so it gives us this horrible noise in the data. So that can be very problematic, but on the plus side, it's actually quite easy to spot in our data. So if we have a nice clean sounding curve, it might look like this. But if we have our noise, then we will see a lot more oscillations in the data. And we immediately say, there's something here that is causing a problem. We're going to have to shift our measurement. The other type is called galvanic coupling. And this is a slightly different one. This is where we have a completely conductive loop. So it could be like a metal building, or the example they've shown here is metal pylons that have wire across the top to stabilize them, stop them flexing too much. And what happens is that if we're too close to that, when we create this big magnetic field and then collapse it from our transmitter loop, we induce a current that goes up the pylon, across the stay wire, down the other pylon, back through the ground. And it just keeps going round and round and round, gradually decaying over time. And so the problem that causes us is that actually just looks like something conductive in the ground. So we need to be very aware of what is around us when we do the survey, because this would be our nice clean curve. And then if we had something conductive nearby, what it does is it pushes the response out to the right. And so effectively shows us that we're getting a stronger signal back, and a stronger signal back suggests that there's something conductive nearby. But we don't know whether that's in the ground or whether that's something 30 meters behind us. So we need to keep our eyes open when we do survey to these potential sources of noise. And so this is just a kind of real world example of 3 TEM soundings that have been taken towards and then past a farmstead. So this first sounding is out over here on the left-hand side, and you can see we've got a nice clean decay curve, no problem with that at all. And then the third sounding is taken out on the right-hand side, and we've got a nice clean curve through most of it. We've got a bit of this capacitive coupling where we get the spikes right at the end, and that's probably coming from this little building down here. But the one in the middle, which is very close to this track and this big farm, you can see that we've got the capacitive coupling, so it's oscillating up and down. And actually, if you compare the trend of that, the whole thing is shifted out to one side. So we've got a combination there of capacitive and conductive galvanic coupling. So again, when we're planning our surveys, we just need to keep these things in mind. And again, just a case study just shows the kind of effect that can have on the final model. So this is the raw data that we get from a sounding that is far enough away from the buildings. S2 is a sounding that we got when we were a little bit too close. And the resulting model of resistivity against depth that we get will look very different in those deeper layers, i.e. the last part of the sounding where that noise has come in. So that's all the theory. That's how TEM works, what it does. I thought we'd just have a little look now at the instrumentation that Guideline manufacture, the ABEM WalkTEM. So first thing, just a little bit of history about it. The WalkTEM instrument was developed as a kind of ground-based partner to the SkyTEM system, which is an airborne TEM system developed in Denmark and has been used to map the entire water reserves of Denmark as a country. And what they needed was a system that could kind of fill in some of the gaps that they had in their survey on the ground. And they took a number of existing TEM systems to a test site from a number of different companies, and they got them all to run measurements there. And the problem they found was that the response that they got from the different instruments was very different. And so they weren't sure which one would be the best one to use. And so they decided that they would take the question mark out of the equation and take the technology from the SkyTEM system and try and put it into a ground-based unit. And so they came and approached ABEM as a ground-based geophysics manufacturer and said, here's the technology, can you help us put that into a ground-based platform? And so the WalkTEM was developed, and then we were doing all of the calibrations at the same site that the SkyTEM system has been calibrated on. And the SkyTEM system is used all over the world for water and mineral prospection. And so the WalkTEM kind of followed on as a ground-based version of that. So looking at the original WalkTEM, the system components involved having a single unit that had the transmitter and a receiver inside it. We then had options in terms of receiver loops, so we could have a small and large receiver loop. And key to the design of the instrument was that we could connect both of those at the same time. There was a large choice of transmitter loops, again, for being able to increase the size of the pulse and therefore measure very deep, or to be able to have low current system where we could just measure in very high detail the very near surface. And if necessary, we had the option of an external transmitter to increase the amount of current even further for very deep surveys. And the main advantages I've listed here, which I'm going to come back to in a minute, but the one that I really want to focus on is the dual moment measurement capability. So what we've been talking about with our pulses is that when we switch the current off, it's not an ideal world and the current doesn't disappear immediately. And the problem with that is that we can't take a measurement until that current has disappeared. So if we use a high current, we have to wait longer for that pulse to completely disappear before we can start taking our measurement. And that means that we lose the near surface information, because the longer we wait, the deeper those eddy currents are getting, and therefore the less we know about the near surface. So if we can use a smaller current, well, in that case, it will take less time to switch off, and that will actually give us some extra data. But the problem is that if we use the small current, we can't get as deep. So what do we want? Do we want to have a deep measurement but lose the near surface information? Or do we want to have a shallow measurement and know exactly what's going on at the top? Well, the obvious answer is we really want to know both. I mean, that would be the ideal situation. And so in the WalkTEM, we use this dual moment operation where the instrument automatically flicks between high current, high moment, and low current, low moment. So high, low, low. And then we actually allow the instrument to seamlessly put all of those together into a single outputted file. So we have the high moment giving us the depth and the low moment giving us the near surface detail. So one thing that one of the reasons why I didn't want to focus too much on the capabilities and the functions of the WalkTEM 1 was that actually we're at a stage now where our second generation instrument is almost ready to hit market. Unfortunately, due to the current pandemic situation, which sees me giving webinars from my spare bedroom, due to that, we've had to push back the official launch of the instrument, but we have some key partners now using a WalkTEM 2, and it's kind of the natural evolution of the WalkTEM 1. And so the key advantages that we have with the WalkTEM 2 are, just like the original system, we have this dual moment measurement for shallow and deep. We have 2 measuring channels, so we can use small and large receiver loops. So again, small loop focusing on the shallow detail, larger loop picking up those deeper, weaker signals. So again, giving us the full range of data in just a single measurement rather than having to take more than one. With the WalkTEM 2, we've actually now separated out the transmitter and receiver. So whereas before they were both in the same box, we've actually found that we can really improve the amount of noise that's in the signal by separating those 2 out. And that actually allows us then to measure even deeper without having to increase the current, without increasing the loop size. So that's giving us cleaner data. It also gives us more options when we're defining what kind of system to sell to someone like you, the customer. You can tell us how deep you need to go and what you need to be looking for. And it gives us more options in terms of the size of the transmitter, how the instrument is set up, the functions that we have on the receiver. Again, like the original, we have onboard inversion. So that allows us, as soon as we've taken the measurement, in the space of a couple of minutes, just to invert it on the machine automatically, look at the model, and basically have a good impression of what's beneath our feet. And also, it's a good quality check. You know, have we taken a good sounding? Are we going to get back to the office with something that we can use? We can go up to 20 amps with the regular transmitters. So that's slightly more than the old system, which was 15. And so 20 amps is, you know, it's a sizable increase in terms of the amount of power that we can generate. So that's good because that means that we can go more powerful before we have to step up and invest in the into the TX60, the other big external transmitter. We have far more options in terms of what the receiver and the transmitter combinations are. So again, hopefully we can tailor exactly the right solution for you. Like the WalkTEM 1, it's got onboard GPS built into the handle. But what we also have now is onboard damping resistors and the ability to analyze the shape of the switch off on our pulse, which, if you've never used a TEM system, it probably doesn't mean very much to you, but it allows us to make sure we get exactly the right setup for the system the first time. We don't have to take lots of test measurements. We can just do this one waveform test, select exactly the right damping resistor to tune the loop to the ground that we're working on, and then we're underway doing our measurements. And finally, we can also record more than just the vertical component. So originally, the original WalkTEM was only set up to take a measurement with the loops laid horizontally, so measuring the vertical component of that as a secondary field. But now we can actually turn those antennas on their side and measure the X and Y components as well. So it's quite a big step up. We're really proud of it. And hopefully once we can get through the end of this pandemic, we can do the big official launch on it, and you'll hear a bit more about that. So I'll just flick through these. As I said, the instruments have the inversion software on board, and the inversion software that we use is called SPEAR, and that is from a company called Aarhus Geosoftware. And on the instrument, it's an automated function, so it is looking at the data, automatically deciding what good and bad data points are, and then giving us our inversion. So on the instrument, you would see the window pop up. You just press a single button, window pops up, and all we have to do is hit run inversion. It'll automatically go through, filter out the bad data, run the inversion and present us with the model. And it will tell us what our depth of investigation is. So you can see here on this example, it's 246 meters. And also then give us something of our data residual, tell us how close that model might be to reality. There's then also a PC version, which actually allows you far more control. You can do the filtering yourself. You can edit the model. You can rerun the inversions. And it also allows us to actually now look at IP information based on the shape of the decay that we're getting. All of the stations get shown on in survey maps. And we can actually try lots of different models on the same data set with, using maybe just one of the receivers or a different selection of data points, and we can compare them side by side to really try and get the best refinement of our model. And we can add any kind of information that we already have. So we can fix layer depths, we can fix resistivities of different layers before we start the inversion to try and get a more accurate result out at the end. And then a really nice, neat feature is that we have a single button report function. So we just press that and it'll output a PDF with header information about instrumentation, date of survey, type of survey that was done. It will give us the raw curve, the model, and then a table of values for layer resistivity and layer thickness. All that single button press. So really nice, well-designed package of software. So let's just have a little look at some data examples. This first one comes from very close to home for ABEM. It's from Scandinavia, and this is looking for quick clay. So it's a big problem in Scandinavia where you have this marine clay. It has a lot of salt in it, and when the salt is in the clay, it's nice and rigid. It's good, strong clay. But over time, what happens is that the salt dissolves and gets washed out of the clay, and that removes the structure from it. And you may have seen in the news, it was a couple of months ago now, there was a very big landslide in Norway where like an entire side of a hill slipped out into the water. And that's a quick clay problem. And so what happens is once that salt's gone, if you apply pressure to that clay, it can just very suddenly give way and liquefy and slide off. And so what they were doing here was trying to identify the regions where the clay might be problematic. So you would expect clay to have an incredibly low resistivity if it's got salt in it. So we're talking, 1 ohm meter, could even be less. But when the salt gets washed out, then the resistivity will start to increase. So they know that the geological sequence in this region is this salt clay. And so all they have to do is identify where the resistivity inexplicably jumps up, and then they can test that with more intrusive methods and work out some kind of mitigation strategy. This is a groundwater survey, so this is very common use for the TEM, and this is from East Africa, and this is probably the best data I've ever seen from a WalkTEM using just a 40 by 40 meter transmitter loop. So single strand wire, 40 meters, 40 meters, 40 meters, 40 meters, and then our 2 receiver loops in the middle. And what they were looking for was fresh water. And they were also interested if there was any regions where there may be kind of saline pollution, salt water entering the aquifer. So they know what kind of resistivity values to expect for water-bearing rock. So those have been highlighted in blue, and then in red, this is the region where they expect there to be some kind of salt intrusion because the resistivity values have dropped very, very low compared to what you would expect for that particular geological unit. Now, the depth of investigation, you may not be able to see this very easily on your screens, but it ranged from around 300 meters down to just over 400 meters with what was a very simple setup. So the WalkTEM unit, 40 by 40 meter transmitter loop, 2 receivers and 12-volt battery. But this was perfect conditions, very highly resistive, homogeneous overburden going into an aquifer with low resistivity. So as we looked at before, current passes through that resistivity, high resistivity top layer very quickly, and then gets and sits in that lower resistivity region below very, very easily. And then this is just an example that actually takes data to the next step. And this is using another piece of software from Aarhus Geosoftware called Workbench. And in this region, they were taking a series of profiles with their TEM system. So each one of these black dots is a TEM sounding. And what they were able to do is then plot the data from that profile, so you can see it across the landscape. Then apply a geological interpretation to that so that you can get a really clear picture of how the geology changes from this riverside location back inland. And another thing that they were able to do with this data, because they had a relatively good spread of soundings, was to generate resistivity slices. So you take the 1D soundings that you've got, and then you can do a constrained inversion that actually allows you to map how the resistivity varies in plan rather than just vertically, and generate these maps of resistivity that get deeper and deeper. And what you'll see is that the reds are the higher resistivity areas, the blues are the lower resistivity, and then you've got greens and yellows in the middle. And where the colors disappear, that's the point where the soundings reach their maximum depth of investigation. So the instrument is always telling us that, and the software just automatically cuts off anything beneath that. So it gives us a very quick and easy way to look at how the resistivity changes over a very large area. If you imagine trying to do this with a VES survey, that would be a huge amount of work. With the TEM system, 15 to 20 soundings a day is not out of the question. Let me just drop into here. Oops. So just coming out of I want to come out of that presentation for a moment. And I want to just finish off by just showing you the software packages, just a couple of minutes. And so this first software package, this is SPEAR. This is the 1D inversion package. So this is just taking the data straight from the instrument and running our inversions on it. So if I look at some of the raw data, we can see that we have one project here with 3 measurement stations within it. So 3 separate soundings. If I hit the little map icon, we can see where those are on the map, like that. And actually, all of these have been taken at the same location. So it's probably just trying different measurement scripts, different loop sizes at one position. And then if I click on one of the soundings itself, one of the stations, then I get to see the data. And you can see that there are 8 channels of data here. So channel 1 is the low moment, the low current on the small receiver. Channel 2 is the high current on the small receiver. Channel 3 is the low current on the larger receiver, and channel 4 is the higher current on that same receiver loop. So we have all of that data combined in this one plot, nice and easy to deal with. And then the other channels are noise measurements. So that is just recording what comes in on the receiver loops without any current pulse whatsoever. And so that allows us to know when the signals that we're recording are falling into that background noise, and so where we should stop trusting the data. So there's lots that we can do with this, but I'll just quickly go through the basic process. Effectively, what I would do is look at each of my channels and I say, right, low current, small loop, this isn't going to be very good for the deeper data, so the later time gates. So I'm going to tell it that I don't want to use that late stuff in the inversion. Then the high moment with the small loop, same thing, it's not really going to be all that good on the later gates. So remove those, say not in use. Then with my big loop, well, I don't trust anything that's in the kind of very early times, because that big loop might still have a bit of residual current induced in it by the transmitter that it's trying to get rid of. So I just say not in use, but I'll leave the rest of that heading down there. And then the same with the high moment on that. I'm probably just going to ignore the first few gates on that and just say not in use. Then gets a bit noisy at the end. We could get rid of a few of those. So if I go back now, anything that's gray is going to be ignored when we do the inversion, and anything that's in color is going to be used. So we just hit the inversion tab and tell it to run. And from the webinar I did this morning, I found that my poor old computer struggles with streaming and inverting at the same time. So this is a fairly painful process, but bear with it. So now it's taking all of those 4 data streams and it's going to use those to run the inversion. And I can, once I've run the inversion and looked at the model, I'll get a residual from that. So I'll have an impression of perhaps how reliable that model would be. And then I can go back and really refine this and say, okay, I'm going to take out these data points here, or I'm just not going to use one of the loops for a certain section, and then run the inversion again and see how that's changed it. If I have any prior information, I can basically stick that in up at the top here. I have the ability to edit the starting model where the software begins when it does its inversion. So I can say certain layers should be a certain resistivity, or there should be a change in layers at different depths. We can actually manually change the model as well. So the inverted model, we'll see it on the right-hand side in a few seconds. We can actually just grab the parts of the model and just drag them around with the mouse to see how that affects the fit between the raw data and the inverted data. So here we go, it's done. So if I click on the model tab, I can see I've got a residual of 0.5 here. It's not brilliant, but it's okay. I've got 4 layers and the depth of investigation on this particular site is 81 meters. So we can see our resistivity values coming down here. And as I say, if I want to, I could actually edit this model. So I can click on a particular part of the model and drag it. And when you let go, it will then update in the diagram what it says that, you know, the curve would look like with that model. So you can try and tweak the model, you know, split these layers to add more in, and then run the inversion again once you've edited it closer to your raw data and see if you improve the situation. We can, when we've got our model, we can also just cancel that, save that model as the starting model and then rerun it again. Or alternatively, if I'm happy with it, then I can export that to a PDF and it should pop up. And you basically get a 1-page report. So you've got header information at the top, you've got your raw data curve, you've got your model in the bottom, and then you've got the table of values that this model is built from. So you have the resistivity of the different layers, the fit for each of those layers, the thickness, the fit for the thickness, so how good each of those are, and then also the depth to the bottom of each layer. And when you export this PDF, you also get this table in an Excel version as well. So very easy to use, very quick to do the processing when you're not trying to stream a webinar. So let's just finally have a quick look at Workbench. So I say this is a much more comprehensive package, but it doesn't actually do the inversion. So you do all of the inverting in Spear, and then you can import your soundings into this package. So if I click on that button, you should be able to see each of these green dots is an individual sounding. I've got one selected at the moment, and if I say show data, it will show me the model data from that particular location. Because it's like a GIS, I can actually import stuff like aerial photographs, as we've got here, mapping data, so this just shows the primary roads. I've got a borehole database, so these black dots are where there are geological logs that I could then compare with my data. And then once all of that information is in, I can start to do stuff that's a bit more complex in terms of viewing the data. So I can generate profiles. So I just simply draw a line through the data and then plot those. So here is that profile A, the one on the right-hand side there. And what this is showing me is the resistivity along that line. And format object, it's just elevation. So each of the soundings is shown by the kind of coarse vertical stripes, and then the smoother one is the profile that we've generated. And what we're looking at this site is an old river channel that cuts through thick clay deposits. So the blue low resistivity is the clay, the red purple high resistivity are sands and gravels that have been laid down by this ancient massive river. And we can see that we've actually imported one of the borehole soundings, so borehole logs, so that's this one here. And even though it's about 50 meters away from the line of the TEM soundings, you can see that there's a pretty good fit. The sand and the bulk of the sand and gravel is shown by this orange color here, and that coincides nicely with the highest resistivity values that we've got from the TEM data. We can go a step further. We can actually generate the slices that we looked at in that case study. So this is the average resistivity from 0 to 10 meters below the surface, 10 to 20, 20 to 30, 30 to 40. And what you'll see as we start to get a bit deeper is that we have kind of silt and till on either sides. And then in the center, we have the sands and gravels. And that channel will gradually get narrower and narrower through the center until we get to a point where we have actually gone beneath the channel and we're just into the clay. So anything that I'm looking at in that 2D view there, I can also generate a 3D plot from. So rather than just do like a laterally constrained inversion to produce a profile, which was here, my profile, I can do a spatially constrained inversion and generate from my individual soundings a 3D block. And then that 3D block can be sliced at any particular depth or any angle to look at the internal resistivity values in there. And those are just the individual soundings in their 3D relative space. So as I say, Workbench, very, very powerful piece of software. Is a very good method means of importing our TEM data and doing a lot more with it. It can also do ERT inversions, IP, so it does allow you to actually combine other data sets as well. Minimize all those. So that was a kind of whistle-stop tour of the TEM technology, our WalkTEM instruments, and the software that we use for doing the processing. So with that, I'll say thank you very much for listening to me over today, and I'll open it up to the questions that we've received on the chat room.